Hello students, today we will discuss analog electronic circuit DC biasing of BJT. In previous lecture I have already told you that is your fixed bias. In fixed bias what we have observed in fixed biasing scheme. In fixed biasing scheme we have observed the stability factor. In stability factor it is not reliable biasing for transistor as an amplifier. In fixed biasing scheme, the stability factor is not much improved in fixed bias scheme. Then another biasing method, that is your collector to base bias. In collector to base bias, we can say that it is a feedback bias. So in your feedback bias, why the name is so called feedback? This is a input and this is output, and there is a path between output to input. We can say that this is a feedback path. Here the resistor is RB is connected between output to the input here. DC biasing of BJT, there is a capacitor here and also there is a capacitor. Now in a DC, the capacitor is open circuited because and the frequency is 0 and the reactance will be more, and this can be open circuited. In a DC biasing of BJT, what we are going for in case of biasing, first of all we have to calculate the input current, then we will calculate the output current. Input current is your base current here, and this is nothing but base. This is your emitter and this is your collector. First of all, we have to calculate the input current. Input current is your base current. After getting input current, then we will calculate the collector current. Collector current is nothing but IC. So then, in case of DC biasing, the capacitor here, before applying KVL, the capacitor will be what? The capacitor will be open circuited here. The capacitor will be open circuited. If the capacitor is open circuited, how to form a loop here? And this is nothing but what? If you will form a loop, this is your plus VCC, this is VCC with respect to ground. That means this is nothing but what? This is your VCC here, and same VCC is applied both input and what? Now output. The same VCC is applied both input and output loop. And here the current flowing is like this. The current is flowing like this here also, and the current flowing is like this. When we will apply the KVL to the input loop, what is your input current? This current is nothing but what? This is nothing but your base. Obviously the base current flows through this branch, that is your IB, and this current is nothing but what? This is your emitter terminal. The current is nothing but what? That is your IE. Similarly, this current is nothing but what? This current and this current. This is nothing but your what? I. This is your IC, because this is your collector, this is your base, and this is your emitter. So emitter equal to base plus collector. So this is nothing but your what? Base current, this is your emitter current, and this is your collector current. If you applying Kirchhoff's current law at this point, this current equal to this current plus this current. So I can say this current is nothing but let IC dash. So IC dash equal to here IB plus IC. Here IC dash is nothing but IB plus IC. First of all, I will apply Kirchhoff's voltage law to the input. Apply KVL to the input. Apply Kirchhoff's voltage law. Apply Kirchhoff's voltage law to the input. What is my input equation? If you will apply KVL to the input, what is my input equation? First look at this. This is your plus, current entering plus, leaving minus. This is plus, this is minus here. So then if I will apply KVL here to the input, this is your what? Plus to minus minus. First of all, this is nothing but VCC. So here like this, the loop is like this. Minus plus plus, this is your VCC. This is your plus VCC. This is your plus VCC. I can write this is your minus and this is your plus VCC. Minus plus VCC. Again plus to minus minus. Current into resistance. IC dash into RC. Minus IC dash into RC. Then again this path. Plus to minus minus. That is your what? That is your IB into RB. IB into RB. Then here there is your plus and this is your minus. Between base and emitter, always there is a potential we have to take into account. This is your base emitter voltage. That is what? VBE. So then this is your VCC minus IC dash RC plus minus minus IB into RB plus minus minus VBE equal to what? 0. Apply KVL to the input and get the input equation and find out the input current. Input current is nothing but what? Base current here. So this is nothing but what? This is your VCC minus IC dash. The value of IC dash, in place of IC dash, I can put what? IB plus IC, because IC dash equal to IB plus IC. In place of IC dash, you will put what? IB plus IC. IB plus IC whole into RC. Then minus IBRB minus VBE equal to 0. This is my input equation. Then VCC minus, you will expand this bracket, then IBRC minus ICRC minus IBRB minus VBE equal to 0. First of all, apply KVL to the input, find the input current. Input current is nothing but base current here. So this is nothing but VCC minus. So this is nothing but IBRC. 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 This is nothing but, in place of IC, you can put IC equal to beta IB, because IC by IB equal to beta. In common emitter transistor, beta equal to IC by IB. Once you got IC, IB, you can find out the IC, because IC equal to beta IB. In place of IC, you can put what? Beta IB. Beta IB into RC. Then minus IBRB. Then minus VBE equal to 0. Then what we will do? Let this is equation 1 and VCC here minus. This is your IB, this is your IB, this is your IB, and IB taking common. If IB taking common, then the value will be how much here? That is your what? RB. This is your RB plus, that is your what? This is your IBRC. This is your what? Minus beta RC. That is your IB taking common. This is your RC plus beta RC. That is your 1 plus beta all into RC. So that is your what? This is your RB, beta RC plus RC, beta RC plus RC. That is your IB, IBRB. This is your IBRB. This is your IB into RC, IB into RC. Then IB beta RC, IB beta RC. Okay. So minus VB equal to 0. So then this term, bringing the right hand side, it becomes positive, and the value of IB is how much? So IB equal to, the value of IB equal to, that is your VCC minus your VBE divided by, that is your what? RB plus 1 plus beta whole into RC. So this is nothing but what? That is your IB. Apply KVL to the input, you will get the input current. Input current is nothing but base current. Here base current is your IB. IB equal to VCC minus VB divided by RB plus 1 plus beta whole into RC. So this is your equation 1. This is your equation 2. Then apply KVL to the output. Apply Kirchhoff's voltage law. Apply KVL, Kirchhoff's voltage law, to the output. What is my output equation? If you will go from plus to minus, that will be minus. If you will go from minus to plus, that will be plus. So same VCC supplies both input and output. This is nothing but, I can say, VCC. If you will move from minus to plus, that is your plus. Same thing, VCC. Then what? I am going from here anticlockwise in output loop. Plus to minus, minus. Current what? IC dash into RC. So VCC minus IC dash RC. Then here there is a potential. Already I told you, between base and the transistor has 3 terminal. One is your base, another is your emitter, another one is your collector. Between base and emitter there is a potential VB. Between collector and emitter there is a potential what? I can say that is your VC. Already you have to take into account when you will move from either applying KVL to the input or if you will apply a KVL to the output. This is your VB and VC already you have to consider. So here when you are going to apply KVL to the output loop, then my output equation will be how much? VCC minus IC dash RC. This is your RC. VCC minus IC dash RC minus VCE equal to 0. IC dash is how much? IC dash is nothing but IB plus IC. Here VCC minus, in place of IC dash, you can put what? That is your IB plus IC whole into RC minus VCE equal to 0. Okay, or VCE equal to how much? VCE equal to, that is your VCC minus IB plus IC whole into what? That is your RC. So this is my output equation. This is my input equation and this is my output equation. So in collector to base bias or fixed bias or any biasing method, we have to calculate first of all what? Operating point. Operating point is nothing but Q point, the value of IC and VC. How to find out the IC and VC? The transistor will operate a particular value of collector current and the particular value of collector emitter voltage. That's why we are saying the operating point is nothing but IC and VCE. How to get IC? First of all, apply KVL to the input and the input current is your base current. After getting base current IB, then we will calculate the IC because IC equal to beta IB. Here the equation of IB is this one, and after getting IB, then if you multiply beta, you will get IC, one of the operating point. Then if you apply KVL to the output, you will get what? The output equation, that is your VCE, that is your collector emitter voltage. The IC and VC are the two operating points you can find out or you can determine. Then go for the stabilization. To judge the particular bias, particular method is suitable for biasing or not by means of stability factor. In a stability factor expression, in a stability factor, that is your SF. Stability factor is nothing but what? There is a generalization formula for the stability factor. SF equal to 1 plus beta divided by 1 minus beta DIB by what? DIC. That is your stability factor. So to judge or to evaluate or to determine whether the operating point, whether this biasing is suitable for transistor biasing or not by means of stability factor expression, if the stability factor, the value of the stability factor is less, the stability is more. Means the operating point is independent of the variation of the transistor parameters. There are so many, there are three transistor parameters like beta, VB and leakage current. And there is an, if the leakage current will increase, if the transistor will operate, heat is developed within the transistor, means temperature increases. If the temperature increases, leakage current also increases. So every 10 degrees centigrade rise in temperature, ICO doubles or leakage current doubles. At the matter of second, the transistor will burn, and the process is called the thermal runaway. The self-destruction of an unstabilized transistor is nothing but thermal runaway. This type of condition may come if the transistor is not biasing, if you will not choose a suitable biasing method. So to judge or to evaluate or to determine the particular value of IC and VC, if our value of IC and VC is independent of variation of the transistor parameters, the biasing is most suitable for transistor biasing. That means we will get a properly amplified output signal. So here in this case of in collector to base bias, to judge the biasing is suitable for transistor biasing or not by means of stability factor, and the stability factor expression is like this. This beta is constant, and here we have to determine a DIB by DIC. Here, if once we get the value of IB, if we are differentiating this IB with respect to IC, then we will get DIB by DIC. So how to get DIB by DIC? When I have applied the KVL to the input expression becomes what? IB equal to, that is your VCC minus VB by this one. And here in equation 1, this IB is not containing the term that is your what? IC. That's why in equation 1, to find out the stability factor, that is your what? We have to find out IB with respect to IC. means dIV by DIC. From equation 1, this is your IV and this is your IV. Not convert IC into beta IV because we have to differentiate dIV by DIC. Here, if you will not get IC term. This in equation 2, there is no IC terms. This equation is valuable for what? For determination of the base current IV. But to judge the stability factor, you have to take this expression because I have converted IC into beta IV. That's why there is no term in containing IC. To find out the value of IV, you can take this equation. But to find out or to evaluate the performance of the biasing method, to find out the dIV by DIC, you will take this equation, that is your what? IV in terms of IC. What I am trying to say, this expression, the base current IV in terms of IC, so that we will differentiate this IV with respect to IC, and I will put this value and then determine whether this biasing method is suitable or not. From this equation 1, that is your what? I am separating the IV value here from 1, that is your VCC, minus, that is your, if IV taking common, the value will be how much here? That is your what? RC, and this is your RB. First I am writing RB, this is your RB plus RC. Then that is your what? Minus ICRC, minus ICRC, minus VBE equal to 0. Or a value of IB is how much? IB equal to this term, bringing the right hand side, it becomes plus. So IB value is how much? VCC, this is your VCC, minus VBE, minus ICRC, divided by what? RB plus RC. And this expression, what I am generally taking what? For what? To judge the stability point of view. And this equation, and this is your what? This is nothing but what? This expression, if you are differentiating this, differentiating equation with respect to IC, what I will get? If you are differentiating this dIV by DIC, so dIV by DIC is how much? dIV by DIC will be how much? dIV by DIC equal to, remember the VCC, here this VCC is a constant, VB is a constant, VCC 20 volt, 15 volt, 10 volt, whatever the value, any derivative of constant will be 0. This is constant. VB is 0.3 germanium, 0.7 for silicon transistor. This will also constant. This will be 0. Differentiating the constant, the value will be 0. Then here dIV by DIC, with respect to IC, the value will be how much? Minus RC by RB plus RC. So if you are differentiating this, VCC by this, minus VB by this, minus ICRC by this. VCC is a constant, VB is a constant, and this value, if you are differentiating this with respect to IC, that value becomes what? That is your minus RC divided by RB plus RC. RB plus RC. This is your what? dIV by DIC. Then I will put the value of dIV by DIC in this expression. The value will be how much? That is your the stability factor expression is how much? SF equal to that is your 1 plus beta by 1 minus beta dIV by DIC. The dIV by DIC here, what we have got in dIV by DIC? So dIV by DIC is nothing but that is your minus RC by RB plus RC. In place of dIV by DIC, I will put what? Minus RC by RB plus RC. Minus RC by dIV by DIC is nothing but minus RC by RB plus RC. So that will be how much? Minus minus plus. So stability factor SF equal to 1 plus beta divided by 1 minus minus plus 1 plus beta RC divided by RB plus RC. This is my stability factor expression for collector to base bias or feedback bias. Then we will go for analyze whether this biasing is suitable or not. So this is your RC in that is your collector to base bias or feedback bias. The stability factor depends the two resistors. One is your RB, another one is your RC. So 1 plus beta by RC plus RB plus RC. As for a design point of view, the value of RB is much greater than RC. The value of RB is much greater than RC, stability point of view. So value of RB may be 470 kilo ohm or 250 or like this, and RC value is very less, like 2 kilo ohm, 3 kilo ohm, 4 kilo ohm, 10 kilo ohm, like this. And there is a certain parameters how to choose the value of RB and RC. But factor is what? RC by RB plus RC. The RC by RB plus RC. The RC value is very much less than RB value, and the factor will be how much? That is your, here the RC by RB plus RC, the value of RC is small and RB is more, the value of RB is much greater than RC. If the value of RB is much greater than RC, that is your what? This is nothing but this denominator is more than the numerator, and obviously the value will be what? Less, and you will get some improvement of the stability factor. So already I told you, if the value of the stability factor is less, the stability will be more. And here if you analyze the collector to base bias or feedback bias, and this factor determines the stability point of view. If you choose a proper value of RB and RC, somewhat feedback bias may be improved or better than your fixed bias, because the value of RB and RC, and RB is much greater than RC, and this factor is more, so that this value will be what? Somewhat less and somewhat more, and the value of the stability factor will be less. And this biasing method is not an universal, it is better than your what? Fixed biasing scheme. In fixed bias method, the stability factor is 1 plus beta, but in case of collector to base bias or feedback bias, the stability factor is your what? That is 1 plus beta by divided by 1 plus beta RC by RB plus RC. The stability depends on the value of RC and RB, and if this value is the stability factor is less, by the proper selection of RB and RC, the stability can be improved, so that in case of feedback bias or collector to base bias, the stability is improved, and it is wise to choose the feedback bias rather than what? Fixed biasing scheme. So now in next class we will do more and more number of problems related to feedback bias or collector to base bias. Thank you.